omega, big theta, and also I mentioned small o and small o. For example, I'm going to review the definitions. Let's say if I want to compare two functions, fn and which relation. Supposedly that the running time of 2 hours, we want to know. If we want to know whether it should be big O or theta or omega or theta or small. So you can as I said, you can assume that big O is like less than or equal. I mean, if Fn is the big O of Gn, this means Gn is larger than Fn, asymptotically. And if it is omega, so this is larger than. And if this is a theta, what is a theta? Equal, right? So it's consider this as. You still remember if this is small o? Small o means absolutely small. So there is not positive, it's not equal, there is no equal. And small omega is 9. Again, only these three is required for the exam. But you will see that you will use that for the small one. And this is the most common use in there. For example, n log n is always big O n squared. That's small O n squared. So it tells you absolutely which one is better than the other. So now if we have two functions like f, and let's use an example. If I have two functions, fn is c, example if I have a so if I have two functions, I want to know which one is, or what's their relation, which notation I should use. So we have two rules. One is, before you compare this, for each function you want to drop the low order term. Okay. And the second is ignore the leading constant. So for example, if you have a running time on this function, eventually you would want to write, you ignore the leading, you drop the low order term, so this one is the low order, this one, so you only treat that squared. And then you ignore the leading constant. So eventually you will have a Tn. You can write this is theta n squared. So meaning n squared dominates all the terms. And similarly, when you compare these two functions, you only need to compare. This is you can write this is almost n squared, right? What is it? N log n. So you only need to compare these two terms. And so what is the which is what? What's notation here? Okay. Which one is larger? F is larger, right? I should write something like this. So here we have. general rule is logarithmic log. Logarithmic function is always smaller than polynomial. It is always smaller than exponential. So in other words, if you have a log n, this is always less than n to the b, always less than c. A larger than 0. So the logarithmic function, whatever it is, 100, 1,000, whatever b is, as long as those are both positive, this is always larger than logarithmic. For any exponential, as long as c is larger than 1, it's always larger than 1. Questions? Okay, let's again do an example. I write many functions. Let's tell which one is bigger. Well, we have these numbers. Which one is the smallest one? Which one is the smallest? Let's write from left to right. 2 to the 100, right? Because this is a constant. So a constant always. What's the next one? Which one? Log, right? So I have 2 log. What's the next? Which one? Square root of log, right? Square root. So if you have a difficulty to know which one is bigger, using the following way to answer. So if I want to compare these two, because I have 2 log of it, so it's not quite clear. Okay. So I will replace log n by another m. Suppose log is equal to m. And therefore this one is log m. And this one is square root of m. Right? A square root of m is m to the 1 over 2. So again, you will have this rule. Right? So this one is. In fact, from left to right, it's not even, not only big or it's small. It's absolutely small. What's the next one?
Log n.
Okay. Again, if you have difficulty to know which one is bigger, you replace log n by m. So this is the m1 over 2, this is the average. What's the next? Yeah, so this is not an offense. What's the next? Square root of n, right? Square root. What's the next? N, right? Next?
N to the power 1. N to the power 1.
N to the log n?
N log 1.
This one, right? N log q. Yeah, so there's another one. So
N to the 1.5 and N to the
next
2 power n.
2 power n. Question. Do you know this should be good? Again, if you have some, when compare these two functions, you have difficulties, and use this approach to replace that by another variable, and use this. Okay, I think this is what I think about implementation. It's called rules of functions because this notation is actually studied when n goes to very large, which one is bigger. That's why it's also called rules of functions. If you remember the definition of this, when we have these two functions, we only care when n becomes very large. What's the relation between those functions? That's why we could ignore the order terms, because as n goes to very large, only the highest order term dominant. And also, you will see that although this approach to describe the running time is very effective in most of the cases, you will see that we make so many assumptions. So we have this function, but we ignore lots of terms. And we only study the worst case, and we only, for each operation, we just assume they take the same time. I mean, these assumptions actually is not quite accurate in practice for a specific problem. And that's why when in specific applications, sometimes this may not be good, but in general, this is a good approach compared to algorithms. Okay, the second topic is on algorithm design techniques, which is divide and conquer. And we know that there are 3 steps for this divide and conquer. The first one is divide. What is the second one? Conquer, right? Conquer. Third one? Divide. And this step, remember that this step is actually a recursive step. So we want to divide the problem into sub-problems, and then for each sub-problem, you solve it. And then the last step is combine. So you combine the sub-problem to the solution, or you combine the solutions to the sub-problem into the solution to the original problem. And this step is you divide until the input size is small enough. Small enough means, for example, it becomes constant. Then you solve the problem in any kind of straightforward algorithm. So in general, we use a recurrence to describe running time. We have a Tn b plus f. So if you look at this recurrence, it means for this problem, for the original problem of size n, we will divide the input into a sub-problem, and the input size of each sub-problem is n over b. And once you solve a sub-problems, and you combine that, the solution to the sub-problem, and using a fn time. That's why we have this recurrence. And we studied we used three examples to show this technique. The first one is, which is the first one, finding the largest number. Finding the largest number. Namely, give you an array, how do you find the largest number? So it's very easy to have a linear time algorithm if you scan an entire array. But we give a divided function, and we divide the array into two halves by the middle one. And then that's the divide. For the compare step, we compute an array, divide in half, and we compute for the compare step, we compute the largest one on the left, and then we compute the largest one on the right. For the combined step, we just compare which one is larger. So that's the algorithm. It's pretty easy. So what we have the runtime T and A is equal to what is the recurrence equal to?
2D and 2D.
Okay. What is A here? 2, right? Because we have two subproblems. And what is N over what is B here? 2, right? Because each size is N over 2. And plus, what is the time for combine? Just constant, right? So we just return the variable. So that's the constant. What is the result of this recurrency? Okay? Okay. Log n or n? Huh? You cannot do that in log n because finding a largest number at least it takes linear time. Cannot do that inside. And the second problem we studied is the merge sort. So the merge sort is using the same approach. So given an array, what we do is we first sort on the left side. So we'll have a sort release on the left. And let's see, sort release the L. And then we have a sort release R. And then for the combined step, we have these two sort release. We use the so-called merge step to merge these two sort release. So to do the merge, we take the first element from each sort release, so we compare which one is smaller and which one is in the other sort. And then we take the next one and next one. So that takes linear time, and then we will the recurrence is the recurrence. 2t over 2 because we still have to solve problem each input size is n over 2 plus n, right? Because we need a linear time to merge the two sorts. Okay. The third one is finding the largest subarray. So given an array, we want to find the largest conjective subarray such that their sum is maximum. That's the problem. So what we do is the same. We partition the array into 2, and we find the left largest subarray max 1, and the right subarray max 2. And then the max 1 may be here, max 2 may be here. So then the solution in the combined step, we will combine these two subs. we take a look at this sum, which one is larger, for example, this is larger. But the optimal solution may cross this middle point, and therefore we need to find, we call it a restricted version of maximum subarray. Namely, this subarray has to contain the middle, the partition number. And to do that, we only need to scan from that, on the left subarray, the largest continuous subarray with the right end on the partition number, and from the left. So it's like we have two smaller problems. So this step takes linear time, and therefore we still have the recurrency of Tn over T times Tn over T plus. So what is the result of this summary? This recurrency. And all the things. And this one, of course. Okay. So the reason we want to we need a recurrency to describe the running time is that the divided conquer, because the conquer step is a recursive step. So this algorithm is always a recursive algorithm. So the recursive algorithm sometimes is not as easy as the traditional, for example, you have a for loop, so the time is easy to analyze. You just take a look at how many iterations. But the recursive sometimes is not quite straightforward to see the right time. And therefore, we use the recurrency to help you to get the right time. And this is a quite effective way, and this is probably the best way for, not only for divided conquer, but for all recursive algorithms. So the general idea, you define the function t of the original problem, and then you will have a function t for your recursive step. And then you will have a formula, and by solving this formula, you will get the exact running time. Okay. Another comment is that for the divided conquer, the most important step or the key step is for the combine. So normally when you solve, when you see a new problem, you want to use divided conquer. You want to figure out this step first. Of course, you need to. The divide sometimes is very straightforward. For example, in all these three problems, the input is an array, so a straightforward way is partition by the middle. But the question is, how do you combine? You see that for these three different problems, we have three different ways to combine. But the partition is always the same. So you want to make sure the combine can be done efficiently. For example, especially for the last one, the combine step is not that straightforward. So we need some observations on this. You remember that we discussed the observations. Observation is you can simply start from this partition part, go to the left, and find the largest. That takes a minute. This one is the most important. Any questions? And now we have a question, so how to solve the recurrence. Solving the recurrence. Again, solving the recurrence is not only for the divided conquer, but also for other recursive algorithms. And we discussed a few approaches. One is expanding. The second one, what is the second one? Recursive tree. So we give so many different approaches, but these can be used on different situations. The first two, these two are essentially the same. Expanding is just use mathematical one, and the recurrent tree is just the organized expanding procedure by the trees. So it's essentially the same. And as substitution is used when you, substitution is essentially mathematical induction. This is particularly useful when you have a clear target. You want to prove this takes n log n time. That's the only target. And you use substitution. Right? So master theorem is just applied on those recurrences. Master theorem cannot be used on other recurrences. But these two are normally, these two approaches can be used to solve all the recurrences here. But it sometimes quite tedious. And therefore, if you can apply a master theorem, it can be to a direct result. And actually, if you remember master theorem, not only give you big O, but also give you big data. It's time. Okay. Any questions? So you can go over the exam, another exam, the assignment. In my solutions, I have different ways for each problem. So there's also a handout. So PDF, you can look at that. There are also some examples to help you understand this. Okay, so the last topic is on the what's the last one? On the search. Run search. Okay, so divide and conquer is a standard name. So if you read different textbooks, we all call it divide and conquer. But this one, sometimes people still call it run search. As is also a divide and conquer. But you see, as we discussed in class, there are some difference. I call it point search, but not only it's not necessary everybody call it point search. Sometimes they just call it divide and conquer. For example, the first example we use is binary search. Binary search. So binary search is essentially a point search. Some people still call it binary. Okay. So there are also 3 steps for this binary search. The first one is also divide, and the second one is actually prune, and the third one is conquer. So again, you want to divide some of the problem into many subproblems. And then you, based on certain criteria, and you prune a large portion of the input. So it's like if you have an array, you prune half, you only work on this half. So this is the difference from the divide and conquer. Divide and conquer, normally you need to work on both of them. But the prune search, you only work on some. And of course, we want this part to be pruned as large as possible. And conquer is you work on this recursion. And for this prime search, the most difficult part or the most important part is the prune step. So you need to find those criteria such that you can prune this as large as possible. That's the difficult. For the binary search, it's easy that you get the number. If you are looking for number x, you compare x with the middle, depending on the result, you go to that. So that's why we have the recurrency of Tn. Remember what's that?
Tn over
Tn over 2 plus. So Tn over 2 is because every time you would only have, we perform 1/2. So only another half remains. So we work on the other half recursive. And 1 is, we compare this takes constant. That's why we have it. And what is the result? Log, right? Log. If you compare these two recurrences, so everything is the same, except there's a 2. Okay? So if you compare the result, this log and this is the n, so log is much smaller than n. So this is actually exponentially larger than this number, only because we have a 2 here. And that's why this factor could affect the results a lot. The second example we use, and everybody know binary search, and the second one is a difficult problem, which is for the selection. The selection algorithm. So then we're given a set of numbers, we want to find the kth smallest number. So we use a super selection algorithm. So again, we have an array. So we want to find the kth smallest number. So ideally, we want to pick the median. Let's say if I call it x median, and then compare with the k, we can form half of them. But because we do not know how to find the median, so we use another recursive step, namely we form the array into groups of 5. The size of each group is 5. Of course, in the assignment asks you whether 7 work. So 7 is okay, 9 is okay. And then we pick the median of each group. And then we call the algorithm recursively on the median of this. And the good thing is the size of this median is only n over 5. And therefore, the recursive step gets us input size are much smaller than before. Okay, so that's the idea. And using that, we get the linear time and the recursive is the recursive n over 5 plus e. 7 over 10 times n plus. This is only the recursive step. Of course, the major idea for the selection is you pick a number, you pick any number x, and you find all these numbers less than x, and all these numbers larger than x. So because you are looking for the kth smallest number, you compute the number of these numbers and compare I with k, and then you will know whether the kth smallest number is E1 or E2. So that's the major idea of this selection. But again, ideally we want to pick the median as x, but we do not know. Again, if you compare this algorithm with the quicksort, the quicksort will need to work on both sides recursive. But for this problem, you will only need to work on either A1 or A2. But in order to make sure every time you perform a large portion of the input, we want to pick this x such that either one of them is not very small. That's why we have this term. And this term is N over 5 because we call this our recursive relation on the median of those media. And eventually, solving this recurrence we get. So you see that the recurrence could have two terms of t. For this, you cannot use mass theorem. But you can use these three because, again, here, our target is to design a linear time algorithm using substitution is the easiest way to go. And the selection algorithm probably, so far, is the most difficult algorithm we studied in class. So again, the major idea is here. So this idea is only on how to pick these x so that the left and right are balanced. So you could separately remember those two techniques. The third example we show is called a weighted selection. One of the most important reasons that we have to run a search technique is because we have a selection algorithm. The reason is that, so when we try to design an algorithm to solve this selection problem, we want to have an algorithm that help us to compute the median directly. But when we design this algorithm, we do not have that tool. Now, once we have this algorithm, we can use this selection algorithm to compute the median of a set numbers in linear time. And then that's why we will have a standard provided search technique. So, for example, the weighted selection. So every time we take the median of the values, and then we will have two sets of equal size. So now if we pick the median, these two sets are equal. And then based on this problem, we have, for different problems, we will have different criteria. And then you will either go the left or either go the right. So in general, the recurrence is Tn over 2 plus n. And now this n, we get this n because we have a selection out. Every time we pull a half, and therefore this we get order. It's the same as we have assignment in the assignment 3. So we want to find all those feasible values. So the same idea. You take the median, and based on the problem, you decide which side you can be thrown, and work on the remaining side. The remaining side only have a sign of n over 2, and therefore you will have this recurrence. Okay. Any questions?
How do you use substitutions to find the following kind of selection?
You mean why this get ordered?
Yeah, how do you use substitution?
Substitution is you assume Tn is less than C times n. And then you want to use the recurrence to prove this is true. Because you have assumption of this, and therefore you will have n over 5 C times n over 5. Okay. And so this part is T 7 over 10 times n less than want to show that this is less than C times. You want to find C, and by using these two. And using these two, we can get here. So, so I have a Tn less than C times, or 5 plus C times. So this is something I want to prove, okay? You want to find a C such that this is true. And on the left side, this is C times 9 over 10 n plus. And you want to prove this is true. So this is the, so move to the left, you want to prove that this is C over 10 times x. You want to find a C such that this is true. Where is the C? What is the C? C can be any value larger than 10, for example, if I use 10. That makes sense? Yeah, you can look at the example we discussed in class. You need to make assumption, and then using this assumption, you will get some, assume that the recurrency are true for the smaller values of n. And then you use this recurrency to prove that. To prove that, essentially, you are looking for a value of C such that this. Yes?
This will only give you an upper barrel though, right?
What's that?
This will only prove an upper barrel.
Yeah, this substitution only give you an output. But for this problem, we know this the lower one is also n because the input size is n. In order to find the kth smallest number, at least you need to touch each number at least once. Right? That's already n time or omega n time. And therefore, normally as long as you have linear time arrow, it is always off. But anyway, the substitution only gives you R. This is correct. Other questions on the exam? Okay. Yes?
So are most of the questions going to be like find an algorithm, or will we have some of those kinds of questions? I guess my question is, will there be like, do we have to determine an algorithm on the test?
Yes. I will give you a problem, and you give me the algorithm.
Okay.
And I will give you a problem. I give you two functions. You tell me the notation. I will give you a recurrency, and you solve it.